This is a follow-on to a presentation I made last year where I was introducing the HPCS I/O scenarios that Cray was doing for as part of our DARPA High Productivity Computing Systems program. And so I'm referencing this just quickly. I've got a link to the slides from last year at the end of this if you want to look at it. But the HPCS scenarios were a number of workloads, 14 workloads that DARPA had given the HPCS vendors that we were to use to characterize our storage system that we were providing for the DARPA contract. And the purpose of the scenarios was to focus on scalability. They didn't want us to give a performance number, a peak performance number. They wanted us to demonstrate scalability, which meant that when we did this test for our program, we had to use 3 different size file systems. We had to scale it as units of 1, 2, 4, whatever, so that you could see the scaling of the system. Because peak performance numbers, it's too easy to go on fudge numbers. They just wanted to see how things scaled. So as I said, we gave the slides last year, sort of introduced what the scenarios were about, and then what I promised last year is I'd come back and tell you how we did, what we did to get this ready for the DARPA demo that we gave in October. And we successfully demonstrated the XC30, which is our new supercomputer based on the Ares network, to DARPA last fall. So there are 14 scenarios. I've shown them here. There's 3 basic grouping of them. There's streaming I/O, parallel I/O, and the metadata I/O. The streaming I/O is dealing with the capture I/O environment. It's a type of environment that Cray systems usually don't do very well in. We do very well in the massively parallel programming or programming environments. And so the parallel I/O and metadata I/O were the areas that we focused on for DARPA. As you'll see here, most of these are checkpoint restart, and they're looking at end-to-one or end-to-end file per process I/O. Large to small I/Os really don't make that much of a difference there. Where they do make a difference is in shared file I/O, end-to-one. So a large end-to-one file is, or pattern is doing strided shared files, and then the smaller is doing a the first large one is segmented shared file, and then the smaller one is for strided shared file. And then in addition, they added some tests at the end of it at the last minute for us to look at random I/O. And this is mostly a read test, starting either random reads within the file or restarting at the end of the file and reading backwards at a random distance. Metadata performance is typical things that you'd expect for, how do you walk through a directory tree. And we know that Lustre, prior to the availability of the distributed namespace, the DNE that's just landing in 2.4, we know that that's not going to scale because we only have one metadata server. What we did for our test, from the differences that we made from the tests we reported last year, we had learned at our work at running on Oak Ridge that the original scenarios have been written, described in terms of total volume of data, just to move so much data. They did it based on the multiple of the total amount of memory in the system. And if you do that, that's just non-determinate. You sit there and you'll twiddle your thumbs waiting for the thing to end. So we made a change to all the files, or all the tests, so that there's an immediate exit. We look for a stable state and then we let the test exit. The other thing we did is we improved the command line syntax. We had done this we'd written the scenarios over almost a year, and what we used at the beginning of writing it were a little bit different than the end of it. And so what we did is we consolidated the parameters, and then that made it possible for us to stick this into the automated test suite that Cray uses to have demonstrated the system. And then the last step that we took was to decouple reads and writes. So a number of the parallel checkpoint restart tests had you write a file and then read the file. And we struggled to try to come up with a way of avoiding a caching effect. And the simplest way to do it was to do the write test, end the write test, and then flip a flag and say, now go read that file. And magic happened, and we would avoid the caching effect. All of these changes, the final tests that we use for the DARPA demo are up on our SourceForge repository. The link's there at the bottom of the page. So here's the XC30. I'm not going to go into great detail about it. The biggest thing that it's an extension of Cray's hybrid processing architecture. Just like James was mentioning earlier, we have systems We can put them in with scalar processors, and we can replace the blades, and you have a way of getting to GPUs. We're extending that same architecture, we call it adaptive supercomputing with this. The big change for Aries, though, is really the interconnect. It's the next generation of the Gemini architecture. We call Aries. It's a Dragonfly network. It's all electrical connections within the chassis and between two adjacent cabinets, and then there's optical connections linking up between groups of two cabinets. For us, being Lustre people, what's really most important to us is what's the software stack. Cray does Lustre routing. So we have two types of nodes in the system. We have compute nodes and I/O nodes. Excuse me. The I/O nodes we configure as LNet routers. And so what that means is that the router is using our Aries LND, it's the same thing as the Gemini LND that James was describing, that's inside on the Aries network, and the router node then maps it onto the O2IB LND to get to the InfiniBand cluster. We use Snexion, which is it's a Lustre storage in a rack that we then is sitting on an InfiniBand fabric. So the router, the I/O node is just shuttling data back and forth between the compute nodes and the external file system. Our demo system configuration is that, so this is something we had to set up in our Chippewa Falls facility. We had two groups, which is 4 cabinets. The 4 cabinets are capable of 249 teraflops. And then within that, in those 4 cabinets, then we had 4 I/O nodes. And our I/O nodes have 2 nodes per blade, or excuse me, 4 I/O blades. We have 2 nodes per blade, and we used one of those nodes in each blade to run as a Lustre router. And so I'm showing that in the lower bottom diagram. We used, for the test, although we've got 2 slots, PCI Express slots per node, we only used one of them because our demo was to show 20 gigabytes per second of I/O coming in off of the XC30 demo system. And so we used one FDR-IB connector, or one FDR-IB HCA per node, and we had 4 nodes out of those 4 blades. Our file system was configured out of Snexion 1300. So the system ships, Cray sells XC30s today with the Snexion 1600s. But for the demo system, based on scheduling constraints, we had to move forward with the 1300s, which is the first generation of the Snexion. These use QDR InfiniBand as the InfiniBand connections, and each one of those is capable of 3 gigabytes a second. So to get to our 20 gigabytes a second target coming off the system, we had to have 7 of these 1300 SSUs in the cabinet. The kind of kludge in the configuration for the demo system is that we did have to have an FDR-IB switch to marry between the 4 FDR-IB connections coming in off of the mainframe, connecting up to those 14 QDR InfiniBand connections going off to the SSUs. So the demonstration with the scenarios, we had to focus on scaling. And so to do that, we wanted to come up with doubles of SSUs. So the basic unit is an SSU. That's a 1600, or the Snexion 1300. It's a 5U84 box. And each one of those SSUs, each OSS in that is able to drive 1.5 gigabytes a second. So we took the 7 and we partitioned them up into 3 groups. But using Lustre's OST pools. So we had one SSU as one pool. We took two SSUs and put that in another pool, and then we took the other 4 SSUs and put that into the other pool. So we're able to scale out and double 1, 2, and 4. To drive that and make sure that the configuration was each one of those pools is being driven maximally, is that we used 4 Lustre clients in the supercomputer per OST. So that means for the single SSU, we had 8 OSTs, so we had 32 clients driving those tests, and then for the larger one, for 4 SSUs, we had 128 clients driving that. So here's the first test. I chose 3 samples. There are 14 tests that we ran. I'm just giving 3 representatives here. These match what we showed last year. First one is just an end-to-end file per process looking at large I/O, and it's showing that we started off, we were getting about 3,000 megabytes per second with one SSU. That went up just to under 6 11,000 at 2 and just under 12,000 at 4. So we did get a nice scaling, almost doubling the performance as you double the number of SSUs, and that reads went a little bit faster than writes. Now we looked at random I/O. So the random I/O test, we had to pre-create the file, and then you would start either by randomly reading someplace within the file, or you'd start at the end of the file and then skip backwards. The idea is to see how well the system seeks. The performance on this, we reported last year, we showed really the actual bandwidth is like in the hundreds of megabytes per second. It's very, very slow. It scales, but it's very slow. What's impressive, though, is when you start looking at the number of IOPS. And so when you start looking at this in terms of the reads per second that we're generating, we see a nice scaling from the 1 to 2 to 4 SSUs. And then just like last year, we found that the random I/O work, they actually went slower than the backward reads, and that unaligned were slower than the aligned IOs. Metadata performance, only one MDS. We don't expect to see any scaling. We expect to see very similar results when you're going from 1 SSU to 2 SSUs to 4. And that's what we see here, although we do see a little bit of trailing down at the end of it. I don't have an explanation for that. Oh, and the other thing that happened here is that part of this test, in addition to looking at the scaling effect, is that we were looking at what happens with a cold cache and a warm cache. So the way we ran this is we had a directory tree that we had pre-created on the file system, and then for the cold cache, we'd read it once, and then when we got that timing for that, then we'd reread it again to get the warm cache result. And then the next slide is something that we found, some unexpected results, is that from our pre-testing with MD test, we were expecting the warm cache to be about 10 times faster than the cold cache. But the numbers weren't coming out right. So when we started looking at the intermediate results, we found that even though we were able to go and change the exit time, we couldn't get it down fast enough before the warm cache was out-reading the cold cache. So on the x-axis here, we've got the loop count, which is essentially time, and then the actual data rates there for stats per second on the y-axis. Within very short time, we were getting, the warm cache was doing what we thought. We were getting 10x performance. But then as soon as we got past where the cold cache had already read, then the warm cache was dropping down and essentially doing a cold cache I/O. So what we had to do is when we looked at the intermediate results, instead of changing the time there, we were able to just go and look inside and say, oh, yep, this is the region where it was a warm cache, and we used that to report our results to DARPA. So conclusions from this test, or the conclusions from the study, is that we demonstrated this update of these new tests, and the changes that we made let us demonstrate successfully the Synexion file system to DARPA as the solution for the XC30 supercomputer. Again, we found that Lustre did very well showing scalability. It's just as we all know, is that as you start increasing the number of OSSs in the system, you do get a scalable performance. We look forward to the time when we got D&E and we can actually start looking to see the same kind of benefit of scaling for the metadata servers. The preliminary results look great, and if we repeat these tests with D&E doing 1, 2, and 4 MDSs, we should see similar results. And finally, just to sort of build into the SARP Fest with the benchmarking group, is we presented these to the benchmarking group last year. This is not really a benchmark. It's a workload generator, so letting you look at scaling. That's the whole idea. A lot of people get concerned when they look at these scenarios and say, well, the DARPA is off. It's not realistic to what they're doing. I think the take-home message from this is that you're looking at a scalable solution. You're looking to see how the file system scales. How does your solution scale as you start doubling the amount of hardware you've got? Whether you like the DARPA workloads or not, that's the benefit. And so you can come up with other workloads. It's just that when you start looking at Lustre performance, it's not really a peak that we want to keep showing. We want to demonstrate how Lustre keeps scaling over time. References there, the first one is to our SourceForge website. The second one is to the actual scenarios document that Henry Newman wrote for DARPA a couple years ago. And then the third one is the link to my talk last year where I introduced the scenarios in our tests. And that's it. You told me to go fast, or SARP told me to go fast. So.
Well, it's all SARP's fault.
It's all SARP's fault.
Of course, always.
So if you don't ask me any questions, then it gives SARP more time to go and do his benchmarking working group stuff. But otherwise, I'm happy to take any questions.
Any happy questions? Sad ones?
Okay, well, thanks again for letting me report this back to you guys. I appreciate it.